Hello everyone and welcome to this week's OpenGL water tutorial, and this week we're going to be finishing off our water by adding some soft edges. Before we start though, I recommend that you now use this new DuDv map and matching normal map that are provided in the description of this video, because they actually match each other, and so the specular highlights on the water match the distortion on the water as they should, and it just looks a lot better and a lot more realistic than the setup that I had in the last tutorial. And if you want your water to look exactly like mine, then you can use these constants in the fragment shader and this tiling value in the vertex shader. If you do that, then your water should now look something like this, which may look a little bit too shiny right now, but by the end of this tutorial it will be looking pretty nice with those settings. So the main thing that we're going to be doing this week is finding the depth of the water and then using that to add some nice effects such as soft edges, and we should also be able to fix that annoying glitchy edge to the water. If you remember in the earlier tutorials, we rendered the depth buffer of the refraction render pass to a texture using FBOs, meaning that we already have information about the distance of the terrain and any other objects under the water from the camera. And I've got a visual representation of that depth texture here when applied to the water quad with projective texturing. The whiter a pixel is, the further away that point on the terrain is from the camera. So for any given fragment on the water quad, the refraction depth texture can give us this distance, the distance from the camera to the nearest object under the water. There's also an inbuilt OpenGL variable which we can access in the fragment shader called glfragCord. This contains the window relative coordinate of the current fragment, and the Z component of this variable gives us the depth of that fragment. So again, for any given pixel on the water quad, we can get this distance from the refraction depth texture, but we can also get this distance from the glfragCord variable. If we then subtract one distance from the other, we're left with this distance here, which is the depth of the water from the camera's perspective, or more specifically, the amount of water that's between the camera and the terrain or the object under the water. Once we know this distance, we can use it to add all sorts of depth effects to the water. So let's get into the code now, and in the water fragment shader, the first thing that we're going to do is to add a sampler for that refraction depth texture. Then in the water shader, I'm sure you all know what's coming next, we have to do the usual stuff and get the location of the uniform. So we'll create a new int called location depth map, and then we're going to just get the uniform location, and we're going to spell depth map correctly. And then we're going to connect up the texture unit, so we're going to indicate that we're going to be sampling the depth map, and we're going to be sampling it from texture unit 4. Then in the waterRenderer class, we need to bind the depth map to texture unit 4. So let's copy those two lines. We're going to be binding to texture unit 4, and we're going to be binding the depth map, which we can get from doing fbos.get refraction depth texture. Back in the water fragment shader, we're now going to sample that depth map, and we have to sample it up here before the refraction texture coordinates get distorted, because we don't want the depth map to be distorted. So we're going to sample the depth map, and we're going to sample it using the refraction texture coordinates, because of course it was rendered during the refraction texture pass, and we're going to just take the R component, the red component of that texture, because that's where the depth information is stored. Unfortunately, this doesn't give us a distance. This gives us a number between 0 and 1, which represents the distance that I talked about earlier, but it isn't even represented linearly either. You might have expected the depth buffer value to increase linearly with distance like this, but in fact it's actually something more like this, giving a lot more depth precision to the nearer objects in the scene. So we're going to need to convert this depth value into a distance. So this conversion needs to know the near and far plane values that we use in our projection matrix, and I know that mine are 0.1 and 1000. These need to be the same as the values that you've got in the MasterRenderer up here, and you should really be loading these up as uniform variables. I'm just being a bit lazy here and hard coding them into the shader, but if you have time, I recommend that you load them up as uniform variables. Now we're going to do that conversion, and we're going to calculate the floor distance, the distance from the camera to the terrain under the water, and this here is that conversion. You can copy this down, I've put it in the description, or you can just copy it from the video. I'm not going to explain the maths behind it here, but I've put a couple of links in the description which will explain the maths behind that conversion. So we've now calculated this distance here, but we also need to calculate the distance from the camera to the current fragment on the water's surface, and we can do that, as I mentioned earlier, using the glfragChord variable that OpenGL provides, and we can use the Z component of that to get the depth, and then again we're going to do the conversion to convert it to an actual distance. So we now have the floor distance here, and we have the water distance here, and as I mentioned earlier, we can calculate the depth of the water now by subtracting the water distance from the floor distance. So let's now do that calculation in the code. So we're going to calculate the water depth, and we're going to do that by taking the floor distance and minusing the water distance. So we have now got the water depth, and we can use that to do all sorts of cool effects. But first, we're just going to test that it's all worked by setting the output color of the fragment shader to that water depth, and we need to make it into a vec4, and we also need to make it a lot smaller because that's a distance and we need a color between 0 and 1, so I'm going to divide that by 50 just to make it a bit more visible. And if you run that, you should get something like this, where the deeper areas of the water are white and the shallow areas, especially the edges, are shown in black. So now that we have the information about the depth of the water, we can use this to make the edges of the water much softer. The easiest way is to just use alpha blending and to make the edges of the water quad gradually blend into transparency, and we can add that into the code now. So back in the water fragment shader, let's just delete that last line because we don't actually want our water to look like that. And then in the waterRenderer class, we need to enable alpha blending if we want to use it. So in the prepareRender method, we're going to enable alpha blending like this, using these two lines the same way that we did in the GUI tutorial. And then after we've finished rendering in the unbind method, we're going to disable the alpha blending again. And we can do that by calling glDisable and then glBlend. Let's now go back into the water fragment shader, and we need to set the alpha value of the output color to determine how transparent the water should be. So we're going to set the outColor.a, which is the alpha component, and for now we're just going to set it to the actual water depth. The way that we want the alpha value to vary with water depth should look something like this. At the very edge of the water, where the depth is 0, we want the water to be completely transparent and so have an alpha value of 0. As the water depth increases, we want the water to become less transparent, and then above a certain depth, the water isn't transparent at all and should render just like before. At the moment, we've just set the alpha value to the water depth, so we have something like this. If we now divide the water depth by a certain number, let's say 5, then at that water depth, so at a water depth of 5, the water has an alpha value of 1 and isn't transparent at all. However, the alpha value should then stay at 1 for greater depths instead of increasing more, so we're going to clamp this value between 0 and 1 so that anything above 1 gets clamped back down to 1, giving us something like this, which is actually exactly what we want. If you want to change the depth at which the water has an alpha value of 1, then you can just change that 5 to whatever depth you want. So let's now run that, and you can see that the edges of the water are now nice and soft. Also, the glitchy edges are now much improved, but they're still unfortunately visible. The reason for these glitches is the distortion that we added to the refraction and reflection textures. Before we added the distortion to the textures, the reflection and refraction textures would stop exactly at the edges of the water. But the distortion to these textures means that the cutoff point is no longer exactly in the correct place, and it becomes visible on the water's surface. So if we lessen the distortion around the edges of the water, we can lessen the effect of these glitchy edges. So to reduce the distortion around the edges of the water, we're going to use the exact same code that we used for the transparency, but we're going to multiply it into the total distortion calculation here. And I'm also just going to change this 5 to a water depth of 20 so that the transition period is a bit larger and a bit more gradual. So if you run that, you should now be able to see that that horrible edge glitch is now pretty much completely gone. And I'm going to use that code for one more thing now, and that is to dampen the specular highlights around the edge of the water, because if the specular highlights are too strong, then they ruin the soft edge effect that we've got. So if you run that, you should be able to see that around the edge of the water, the specular highlights get a lot dimmer and so they don't ruin that soft edge effect. Another thing we can do to improve our water is to use the normal vector that we calculated in the last tutorial in our Fresnel calculation. At the moment we're assuming that the water surface is completely flat for our Fresnel calculation, but we don't really want our water to look completely flat. Last episode we generated our own normals from a normal map, so we can now use those normals in the Fresnel calculation. So to do this we first need to move the normal calculation up a bit so that it's above the Fresnel calculation, and once we've done that we can use this normal here instead of the vec3010 in the Fresnel calculation. If we now run that you can see that it has worked, but it looks a little bit crazy, a little bit too extreme. And this is because the normals are all over the place at the moment, making the water seem a lot more bumpy than is perhaps realistic. So we can make the water appear a little bit calmer by making the normals point more upwards, as if the water were flatter. And to do that we can simply increase the Y component of the normals a bit. If we now run that, you can see that the effect is much more subtle and actually looks pretty nice. So we're almost finished now, but that nasty edge glitch is still occasionally visible, so we're going to try and get rid of it completely now. In the main game loop, you may remember that we set up some clipping planes which make sure that the reflection texture only renders parts of the scene which are above the water, and it cuts off exactly at the water's surface. This doesn't leave much room for error, and it's what causes the glitches, especially when the water was distorted. Now that we've dampened the distortion, the glitch is now almost gone, but still the occasional pixel pokes through. So instead of making the clipping plane cut off exactly at the water's surface, we can add a little offset to create a tiny overlap. And you can do this for the refraction texture as well if you need to, but it usually isn't a problem. If we run that, you can see that the glitch is now entirely gone. However, because we've now added an overlap, there will occasionally be things reflected in the water that shouldn't be reflected. The bigger the offset you add, the worse the problem, but as you can see here, there's already a tiny little reflection here that shouldn't be there. So make sure that you keep that offset as small as you possibly can. So that is it for this video and for this series. I don't know if I'm going to be able to do any more tutorials before the Kickstarter now, but if the Kickstarter is successful then I'll be able to move on to topics such as particle effects, shadows, normal maps and text rendering, and then maybe a new series on adding multiplayer support. Don't forget to check out yesterday's devlog video about the new attacks that I've been adding to SOG 1 in preparation for the Kickstarter, and you can get in contact with me via any of my social media pages. All of the links are in the description below. But yeah, thank you guys very much for watching this series through to the end. Do subscribe if you haven't already. Have a fantastic week, and I will see you all next time.